Hi, my name is Samina Mir and I'm master's student in Electrical Engineering Department at San Jose State University. This is my course final project presentation of EE278, which is FPGA implementation of LMS algorithm, which is done under the guidance of Dr. Changchu. LMS algorithm is developed using a FAR filter. The basic idea of LMS algorithm is to modify the coefficients of FIR filter and adapt the coefficients so that the error generated is minimized and converged at the end. So, the reason why LMS algorithm is chosen is because it is robust and very simple. In this project, the implementation is done in two steps. First, the algorithm is developed in MATLAB code and the input samples and desired signal samples are generated. These samples are used in the Verilog implementation and fed as inputs to the Verilog code. And then in Verilog implementation, the FAR and LMS algorithm are used to calculate the error signal and analyzed whether the error signal is converging and minimizing to 0. This block diagram is a basic block diagram of FAR filter with an adaptation algorithm. Here you can see there is a filter and there is this LMS block. X of n is the input. C of n is the coefficient which is given from LMS to the filter, which is every time the input is given to the LMS, it is modifying the coefficient and giving as input to the filter. The Y of n is the output from FIR filter. D of n is the desired signal, and the error signal is calculated using D of n minus Y of n equation. So desired signal is subtracted, desired and the output from the FAR filter is subtracted and error signal is generated, and this error signal is used to calculate the modified coefficient. So the filter coefficients are adjusted in order to minimize the error signal. This is a basic block diagram of LMS algorithm. In this, as we discussed before, error signal is generated by subtracting the output of the FAR signal with the desired value, which is here, and this value is E of n, and this is multiplied with the input sample and also gain factor here. The gain factor is an important aspect of LMS algorithm, wherein as the gain mu value increases, the chances of the error signal to converge are less. For example, if we increase the gain value, the error signal may or may not converge, or it would take more amount of time to converge at the end. C of n plus 1 and C of n are the coefficients which are generated from the adaptation algorithm, and C of n is the previous coefficient value, and C of n plus 1 is the new coefficient value for the data cycle n. Let's go to the first step of this project implementation. Here you can see this is the MATLAB code which is written to generate the input and desired signal outputs. Here, since the output generated from the MATLAB code is a floating point, the code is modified by me to convert the floating point to fixed point here, and also convert the fixed point to hexadecimal value so that it is easier to feed the hexadecimal value in the memory instantiation file. And this is the random input values which are generated in the MATLAB code. This table represents the equations which are used in LMS filter and FIR filter. Here you can see the coefficient values are modified in the LMS filter, and these coefficient values are used here in the FIR filter. So for instance, at first step this value is calculated and this value is passed down to the second step in the FIR filter, and y new value is calculated. So in the same way, every row of this particular table represent the data cycle of the FIR filter. So for instance, in this project we are developing the algorithm for 24 tap FIR filter. So every row represents each data cycle of the filter. So we have 24 coefficients and 24 steps before we arrive the first output from the FIR filter. Since there is a latency of 2 clock cycles to get the values of input values from the memory instantiation file, the first output is generated at the end of 26th cycle in this design. So you can see here the output is generated after 2 clock cycles, so there is 2 clock latency from the memory instantiation file. This is the hardware implementation of LMS algorithm. So here these are the basic blocks which are used in the hardware implementation of the Verilog core. Here you can see there is a data memory block from where we are getting the x of n values. Whenever there is any multiplication carried out in the Verilog, we are rounding it, and also whenever there is a sum, whenever there is a summation happening, we saturate it. So these operations are computed in this MAC filter block, which is like, for example, if y of n is calculated, the rounding is happening here and then it is sent to saturation and the final output is being generated. This value is subtracted from the desired value and error signal is generated. So this error signal is again going to the adaptation block so that a new coefficient is generated from the LMS algorithm. So this loop continues for 24 clock cycles and is executed in a pipelined way. So after the implementation of the adaptation filter, let's go see the output. So here you can see these are the equations which are used to compute error signal and the new coefficients, and so these are the output simulation values which are taken from model sim. So this is the input signals, and this is the error, and the error signal is computed here, and also the H coefficients are also modified in a pipeline fashion throughout the design. After computation of H value, Y value are also computed. So here these are the input signals, input samples, and the corresponding Y values at every data cycle is computed and added at the end. So we are getting the first output at the end of 26th clock cycle. So after computation of H coefficient value and Y of n, we analyzed the error signal. So here you can see this is the input signal which is fed from MATLAB, the random values how they are going, and also desired signal values, and at the end when we analyzed the error signal, it is going random way, and at the end it is converging to some minimum value. Here you can observe that the output of error signal is not completely zero, but it is getting converged to a minimum possible way, and this is happening at 6155 nanoseconds. In this project we are giving around 600 samples of input signal and desired signal, and we are computing the error signal for 600 samples. So after analyzing the results, let's go to Quartus and see a walkthrough of RTL code and demo. So this is the RTL code of the LMS filter, where at every tab to generate the to compute the rounding and saturation, this function is instantiated, and also we are taking values for input and the desired signal from the memory instantiation file, and also we are using a library multiplier every time a multiplication is computed using the instantiation. So every value which is multiplied, we are rounding it so that it is limited to 16-bit, and also this value is sent for saturation, and the output is taken back and fed for the computation of error signal. There's another file which is used where I am calculating the rounding and also saturation, and for the y value to do the saturation I'm computing in other file and calling it in from the main file. So this is the test bench where I'm taking the clock signal. And let's go to the output. So for convenience, I have already compiled the design. So after compilation, when I go to model sim, I have already generated all the signals. So here you can see, as we discussed in the slides, the error signal is not completely zero, but it is converging to minimum possible level, and also the desired signals and Q signals and other signals are shown as here. So this is the presentation of the project implementation of LMS, and the future this project can be extended by adding a analog to digital converter, and also adding some audio file where we can reduce the noise. Like for example, we can adapt the FAR filter, and we can actually see the output of a audio signal with the reduced noise. And also the applications of LMS algorithm include wherein we can find LMS algorithm implemented in FPGA in mobile towers. So there are various aspects. This project can be extended and can also be implemented in hardware. So yeah, thank you for watching.